Okay, you could turn it back on. Thank you. Okay, so now we get the third unit system that we're going to be learning about, and this is called the unit parsec. The parsec is another unit system that helps us measure distances to stars. So we learned AU, light year, and parsec. One parsec is 3.26 light years. So if you compare them to each other, here's one parsec. Let's say this is 1 light year. And then let's say this is the Earth. And then this is another light year. And here's another light year. And here's another light year. So visually speaking, our nearest star is what? 4.2 light years, right? So here's our nearest star. And then the other stars start appearing, you know, like that. That's our closest star, 4.2 light years. Parsec is even larger. One parsec is 1, 2, 3, and a little bit more. So this is one parsec. Okay? So if I want to know the distance to our closest star in parsecs, what would I do? It's going to be like 1 point something, right? Because 2 parsecs is going to be like here. So the distance to our closest star should be 1 point something, right? So what do I do? Where's the, oh. Proxima Centauri 1.29. Alpha Centauri 1.35. Betelgeuse 131. How am I getting those numbers? See, 1 point something, 1 point something. Well, here's how I'm getting them. I'm taking those numbers that we had from the previous slide, and I'm dividing it by 3.26. Right? The distance from Proxima Centauri was 4.22 light years. If every 3.26 light years is 1 parsec, so if I would know the distance of the star in light years, I can divide by 3.26. That's going to give me 1.29 parsecs. And then for Betelgeuse, I'm taking the, what was it? 427, right? 427 light years. And I'm dividing that by 3.26. And what am I getting? 131. Right? So if you are already given the distance to a star in light year, you divide. How about the opposite way? How about if I told you a star is 6 parsecs away from us? How many light years is it away? Now what do I do? Divide or multiply? Yeah. 1 parsec is 3.26 light year. Now I got to multiply, right? So if a star is 6 parsecs away, 6 times 3, roughly 18. So it's going to be something like 20 or so. I'm now going to multiply, right? So if you know the distance parsec, you go multiply, and then you get the light year. Now, the one that's most commonly done is this one. Okay? So when I was giving you the distances to Betelgeuse, to Sirius, and I was telling you they are 8 light years away, they are 13 light years away, they are 400 light years away, didn't you think in your mind, well, how do we know these? How do we come up with those distances? The answer to that question is in this slide. We first do an experiment known as Parallax, and we need advanced computer instrumentation to do this. We find out the parallax angle of a star. From the parallax angle of a star, we determine its distance in parsec. Then we convert to light year, and we know how far away the distance to the star is in light year. So all those distances that I was giving you, we did this experiment on them. Okay? So that's what the next page is describing. So to understand the parsec unit system, you have to understand the phenomenon of a parallax. So where does the parsec unit system get its name from? P-A-R, par, comes from parallax. Okay? So the parsec unit system Parsec, you can kind of think of it as two words. This comes from the concept of parallax. This comes from the concept of arcseconds. Combine the two concepts and you get the unit system of the parsec. So let's understand what parallax means. Parallax is the apparent shift of an object's position resulting from the motion of an observer. So when you are moving and then something seems to be moving. For example, I'll give you a very basic idea. Let's say I'm standing here and I look at you. I have to view you this way, right? And then now I start moving. I have to start shifting my head. So now I go like this. Now I have to view you this way to view you. That's you guys have just parallaxed. Okay? Now, let me compare. Imagine I'm looking at the first student, like here. Then I have to go here, or go over here. Okay, now I'm going to look at the last student. Which one do I have to shift my head more? The first one or the last one? Okay, see here? Like that. It's the first one, right? Last one, I don't have to shift my head as much. So there it is. Now you've understood parallax. When an object is far, the parallax angle of the object is small. When an object is close to me, the parallax angle of the object is large. Here's another analogy. Take your thumb out, look at it from one eye, look at it with the other eye. The thumb will appear to shift. Okay? So do that right now, everyone. And one of the best ways to do it is to, let's say you take the speaker. Imagine you look at your thumb with one eye and it's in front of the speaker, right? If you look at it with the other eye, it's not going to be in front of the speaker anymore. You can take any object that you want. The thumb will have apparently shifted, but it didn't shift, you see? Only my position, my reference shifted. Now, if I bring my thumb closer, does it shift more or less? Try that. Yeah. When something is closer, it shifts a lot more. You see? Yeah, a lot more. As a matter of fact, that's why having two eyes is a very important evolutionary concept. We need two eyes. How can someone tell the depth of something, how far away something is? You use the parallax angle of your two eyes viewing it. Okay, when soldiers lose one of their eyes in war, you know, let's say you lose one of the eyes, what's one of the things that happens? They lose perception of what? Depth. They lose depth perception, okay? And why? Because they can't use parallax. Only this eye is viewing you, right? When you have two eyes, your brain is constantly parallaxing, you see? Like that. So here's one of the things you can try. Close your one eye. Okay, the first student, I'm going to have you do an experiment. Close one of your eyes. Okay, with the other finger, take your other finger out like that. Come and touch this finger. See how much she was off? Now do it again. Now her brain is finally adjusting. Oh, wait a minute. Her brain is saying this eye is not sending me enough information. I got to adjust the distance. Try it again. See how difficult it is? Now open both your eye. Try. It's come from far. Try hitting it with. Now close one eye. Try again. Quick. You see that? Try that with your friends. The reason that your two eyes, they're constantly parallaxing. You see? Okay, so how do we use that in astronomy? Okay, here's a couple pictures here. This is one use of parallax. If I want to know the distance to a tree, and I don't want to have to cross, let's say, a barrier such as a river, I put my platform here. I find out the angle to the tree. This is my baseline. Then I walk over a certain distance. That's my baseline. I view that tree, and then I measure that angle. In this case, the angle came out 90, but it doesn't necessarily have to come out 90. Once I know this angle, and I know this angle, and I know the baseline, I can find out the distance to the tree. Okay? In geometry, they call that angle side angle. Right? As long as you know two angles and a side, then you can know everything about that triangle. Right? This is one example of parallax. Okay? This is how this concept is applied to astronomy. Here is January, you look at a star. July, you look at a star. And the star will have seem to shift its position. You look at it from January, it appears to be here. You look at it from July, it appears to be there. So if you look at it in July, it's here. In January, it's here. It shifted. But it didn't really shift. You see? And then what you do is your baseline is 2AU. 2AU. If you measure this angle and you measure that angle, angle, side, angle, and then you cut that triangle in half. You cut that triangle in half. So then this will be 90. This angle will be whatever you measured. And then this angle is the parallax angle. You see? So in other words, since we know the baseline is already 2AU, then we cut it in half, 1AU, and then we measure this angle and we measure that angle, then we can determine everything about that triangle. So if I want to know the distance to that star, all I have to measure is that angle and this, and then I could measure the parallax angle and I can determine the distance. If the star is close to me, what's going to happen? The triangle is going to look like that. The parallax angle is going to be larger. Therefore, the distance to the star is going to be shorter. You see? And this is a little quick movie clip on that. Okay, so you view it from there, it appears to be here. You view it from here, it appears to be there. Now, the problem with this method is that it requires very detailed computer instrumentation because the stars are so far away, their parallax angle is very, very tiny. I mean, this picture is very exaggerated. The stars are actually way, way, way out there, you see. So their parallax angle, this angle is very, very, very small. So we couldn't use this technique until we got to the age of computers. And then once we got it, then we were able to measure their parallax angle. So the parallax angle of an object is a good indicator of its distance from us. So if an object is close to us, remember the shift is bigger. If the object is far from us, the shift is smaller. So imagine this is the Earth going around the sun. If the star is here, this angle is going to be larger. If the Earth is going around the sun, if a star is here, this angle is going to be smaller. You see, larger, smaller. So distance d, and then we can call the angle theta. Distance d, we can call the angle theta. So the smaller the angle, the shorter the distance. The bigger the angle, the shorter the distance. The smaller the angle, the bigger the distance. Inversely proportional to each other. You see? So the smaller the parallax angle, the farther the object is. Since stars are so far away from us, their parallax angle is so small that it's even less than 1 degree. Remember, what's 1 degree? A circle is 360 degrees. So the definition of a degree, is this is like 1 degree. A whole circle is 360 degrees. But the parallax angle of stars, since stars are very far away, the parallax angle of stars, they're less than a degree. Much, much less. So we need a unit system. We need a way of expressing fractions of degrees. So here's one thing we do. We take a degree and we break it up into 60 equal parts, and we call it arc minute. Now notice how that's related to the regular unit of time, minute. We take an hour, we break it into 60 equal parts, we call them minutes. We take a minute, we take it divided by 60 equal parts, we call it seconds. So this is arc minute. So what would an arc minute look like? Imagine taking this guy. Imagine this is a degree. Taking that and breaking 60 equal parts. I can't even do that, you know. I wasn't able to do it, but you could slice it up. Imagine slice it up. That angle is 1 arc minute. And it's written like that, 1 arc minute. Now imagine taking each of those and breaking up it into 60 equal parts. What are we going to call those? 1 arc second. What is that going to look like? Well, take 1 arc minute. Imagine breaking up 60 equal parts, and that's impossible for me to draw. And each of those, it's like a sliver, like just a line. That's 1 arc second. So divide by 60. You're taking 1 degree, dividing it by 60. You're taking 1 arc minute, dividing it by 60, and you get 1 arc second. Okay? So that's the definition of the arc second. Arc second is 1/60th of 1/60th of 1 degree. Okay? So if you ever are at a party, they give you a pie or cheesecake and you love it, but you're on a diet, say, you know what, I'll only take 3 arc seconds of that cheesecake. They'll look at you, what class are you taking? So they have to take a degree, slice it up into 60 equal, and then that will slice it up into 60 equal. They'll give you 3 of those, you know. Okay, 1 parsec. So here's the definition of the parsec then. A parsec is the distance to a star Parsec is the distance to a star whose parallax angle is what? 1 arc second. So that's pretty easy, 1, 1. If a star is so far away that its parallax angle is 1 arc second, the distance to the star is 1 parsec. That's the definition. And the equation is the distance to the star. Remember how they are inverse proportion to each other? 1 divided by parallax angle. The smaller the parallax angle, the larger the distance to the star. But the weird thing is this. Earlier on, we said that our closest star to us was Proxima Centauri. What was the distance of that star? Yeah, 1.29 parsecs, right? So what does that mean? That means that that star is actually farther away than this point, a little farther away. Therefore, what is the parallax angle of that star? Less than 1 arcsecond or larger than 1 arcsecond? Yeah, because since it's larger than 1.29 parsecs is larger than 1 parsec, the parallax angle of that star is going to be even smaller than 1 arcsecond. So that means we do not have any stars for which their parallax angle is 1 arcsecond. All of the stars that we know of, their parallax angle is less than 1 arcsecond, like 0.8, 0.7, 0.6, 0.5, 0.1, and so on, right? So let's do a quick example. Let's say I told you there is a star whose parallax angle is 0.1 arcseconds. 0.1 arcseconds. What is the distance to that star? Okay. You have to do 1 over 0.1. That's it. Yeah, it's going to give you 10 parsecs. 1 over 0.1. How do you do that? Well, move the decimal point over, and then you just get 10, right? 10 parsecs. That means that star was 10 times farther away than this point. 2, 3, 4, 5, and then so on and so on. 10 times farther away. That star was really far. Okay? Now, if I want to know how many light years is that, what do I do? 1 parsec, 3.26 light years. So 10 parsecs is what? Multiply this by 10, right? 32.6 light years. And then I can keep doing that. If a parallax angle of a star 0.01 arcseconds, 1 over 0.01 gives you what? 100 parsecs. How many light years? Okay. And then if you go 0.001 arcseconds, 1,000 parsecs, which is what? 3,260 light years. Now, presently, our technique of determining parallax angle is probably limited to this range. If you start going smaller parallax, our computers are not able to determine that. Smaller parallax than that. So this technique of finding distance to stars kind of works in this area, up to 300, up to 1,000, maybe up to 3,000 light years, but not more than that. We have other techniques that are useful for things that are farther away. Okay? We used other techniques, but for this technique, we're limited to about 1,000 to 3,000 light years. Okay, so here's an example too. Find the distance to a star whose parallax angle is 0.0124 arcseconds. So in other words, it's somewhere, not exactly 0.01, but it's somewhere a little bit bigger than that, 0.0124. So on the quiz, you're likely to have a question like that. So you take out your calculator. What do you do? 1 divided by that number. Okay? So 1 divided by 0.0124, you get what? Your calculator will give you 80 parsecs. Right? If you just do this divided by this, 80.65 parsecs. And then you're going to convert to light years. How do you convert to light year? Multiply by 3.26. So you get 262.90 light year. That's pretty good. So where did that fit in this scheme? Since this number, 0.0124, was a little bit larger than this, it was kind of between this and this, right? Larger than this, smaller than this. So the distance that we got, 262, was smaller than this and larger than that. See? 262 light year fits like here. Okay? So anyone have question how I got that? What did I do to this to get to that? Multiplied by what? 3.26. Okay? So now you know how we get those distances. One of the ways we get them. We do the parallax angle of the star, and we multiply, we determine the parsecs, and we multiply by 3.26. And this is actually a star called Spica. Okay? What is the parallax angle? If the parallax angle of a star 0.00378, try it out on your calculator. I'm going to try it out on mine. Let's see if we get the same answer. Tell me the distance to that star. .4 light years. Anyone, others got that? Anyone not get it? No one is wondering how to get it? 1 divided by 0.00378. Right? And I got 264. That's units of parsecs. Right? And then you multiply this by what? 1 parsec is 3.26 light years. And then it gives me 862.4. And we could probably go up to this technique, use it up to those distances, you know.